big announcement today. What is it?
We are announcing the principal investigator for our upcoming clinical trial, Dr. David Brandman, who is a neurosurgeon at UC Davis, and our investigator at Mass General Hospital, Dr. Dan Rubin, who is a neurologist.
And they're combining to team up with you for a new brain implant to help people speak after a stroke?
Yes, so we're building a brain-computer interface. It's a high data rate modem that exchanges data between a brain and a computer. And the first use case for this is going to be people who can't speak anymore because of paralysis. People who can't speak, can't move their hands, but using a brain implant, they'll be able to communicate their thoughts to a computer and then speak again through a computer.
How does that work? Where does it go in the brain? How does it speak to the computer? Is it just all by impulses?
So actually, carry around a copy of the device here in my pocket. It is implantable. So this little device goes under the skull, on the surface of the brain, and then on here, it's too small to see by camera, but there are 421 tiny little platinum iridium microwires that are each smaller than a human hair. And they can reach down into the brain and record from individual neurons. And so when someone who is paralyzed attempts to move or attempts to speak, the neurons in their brain are still doing what they would have been doing when they could control their body, but they're not talking to anything. But if you put a brain implant in that area and listen to the neurons, you can figure out what the person was trying to do and communicate it to a computer. So in the case of our first clinical trial, someone will be trying to speak. No sound will be coming from their body, but the computer will know what they're trying to say and will produce the speech.
That is amazing. Where do you see this technology going? You're starting with speech, but where do you see the horizon?
It's almost limitless. So a brain-computer interface is fundamentally just a way of getting data out of the brain and into a computer, or from a computer and into the brain. And in some ways, there's so many different problems in medical science, in biology, that we don't have a cure for. If someone severs their spinal cord, we can't grow them a new spinal cord, but we know that we can take their movement intentions and help them control a wheelchair, control a robotic arm. But even things you might not think of, like for instance, whether someone's experiencing chronic pain or whether someone is depressed, those things exist in the brain too as neural activity. And so we can record neural activity related to pain, mood, or even cognition and make that data accessible to a computer so that we can better direct the treatment of people with severe unmet mental illnesses.
This seems to be moving so quickly. How are you figuring all this out? Is it through AI and quantum computing? How are you moving so quickly?
One of the interesting things is that as fast as BCI seems to be moving, the world of AI and edge computing is moving even faster. And so in some ways we get to draft behind this incredible industry of AI advancements and things like NVIDIA's computing power, so that as fast as we can get data out of the brain, there's infrastructure there for us to be able to process it and make it actionable.
What do you say to the people who are super excited about this technology, and then the other side, it's a little scary to them? What would you say to, bridge that divide? It's going to maybe be a game changer for so many people, but others think, uh-oh, this is kind of scary.
I think when a lot of people think about the future of BCI, they're maybe watching the news and hearing about connecting brains and artificial intelligence and augmented intelligence and merging with computers. I actually think that that's the wrong thing to focus on, both in terms of the benefits of it are far off and kind of elusive, and the dangers of it are also pretty far off and ill-defined. But I think that there's a different future of brain-computer interfaces that is much more concrete and much nearer term that I would love for everyone to be aware of, and that's that a brain-computer interface can help people with unmet medical needs. It can turn these biology problems that are hard to solve and could be decades away into technology problems, and it can let us leverage our most powerful technologies to tackle our biggest problems. And so rather than thinking about, oh, I wonder if this or I wonder if that, I would think, in your own life, imagine all of the people that you know who have been touched by depression or bipolar disorder or Parkinson's disease or other conditions that affect their brain. What if instead of having to wait for a cure for those conditions, what if there were a therapeutic device that they could receive now that would help them? And that's, I think, that's where I would love for the dialogue to move, because that's very real and coming very fast.
Anything I didn't ask or you think is important to say, or what's next for you?
Okay, well, I will share a little bit of information that's kind of, we've talked about the clinical trial, and something we didn't talk about is Dr. Brandman, who is leading the clinical trial, is honestly the world expert in speech prostheses right now. And so his paper that published in the New England Journal of Medicine last year represents the most performant speech prosthesis in the world. And it's a tribute to Dr. Brandman and his team that they were able to do that, because they were working with hardware that was invented in the late 80s. And so what we're doing now is we're bringing, like, the world-class physicians that have been working in this field for a long time, hardware that's kind of befitting of their skills. You know, 2024 technology instead of 1989 technology. And the effect for patients is that they're going to be able to communicate faster with lower error rates, and they'll have devices that are completely wireless and under the skin. And I would also just say that our own technology that we're testing in sheep right now, we're doing preclinical testing of our whole data pipeline in sheep. We're pulling down information transfer rates that are north of 100 bits per second. And so 100 bits per second, like, how do we put that in context? Well, the Neuralink system that's been very reported on, their peak information transfer rate is hovering around 10 bits per second.
That's a big delta.
Yeah, we're about to get into a clinical trial for a device that in the lab is recording 10 times more information than the Neuralink device. And so I'm very optimistic for what that can mean in a clinical setting.
Well, we're excited to watch Paradromics. Matt, thank you so much for joining me.
Thank you for having me.